Today we will start talking about the energy and the main application of storage of electrostatic energy, which is the capacitors. You know, as we have learned in the last chapters, when charges are brought together, there is an energy stored in this system of charges. Now, what we are going to do today is we will first consider and introduce devices that store this energy, and these devices are called the capacitors, and we will define their capacitance, and also we will talk about the energy stored in these devices and where does this energy go, where it is stored actually, and also we will consider other variations on these devices, that is when dielectric is inserted in the space filling the distance between these devices. We will also consider about an electric dipole in an electric field and see the potential energy and introduce the potential energy that this dipole has when it is placed in an electric field. For now, we will first talk about capacitance and capacitors. We will introduce the capacitance and its definition, and then we will move to capacitors and their definitions. Of course, capacitors have wide range of applications in all areas actually of electronics, digital electronics, and they are vital components of circuits where energy and charge storage is needed. We will start with the simplest of capacitors or capacitance. Okay. We will start first with a single conductor, and we will define the capacitance of this conductor. Our conductor will be a specific example, which will be a charged sphere. So it's a sphere with radius r, and it carries some charge on the surface of that sphere. Now, what is the potential of this sphere? As we have seen before, the potential of the whole sphere is constant and is just kq over r, where q is the total charge on the sphere and r is the radius of the sphere. So the whole sphere is at constant potential, and this is equal kq over r. Now, from here, as you can see, the more charge you put on the sphere, the larger is the potential. So as you increase the charge, the potential also increases. Okay, it's evident from here. But the ratio, this happens in a way that the ratio between the charge and the potential is constant. And what is this constant? If you just do it here, if you divide q by v, then the expression that you will get is r over q, there are k over k, r over the Coulomb's constant, and this is just 4 pi r epsilon naught. This is a quantity which depends only on the dimensions of the conductor, which is r, and on the permeability of space. Okay? Therefore, the capacitance, which is the ratio of the charge on a conductor to the potential difference on that conductor, is a constant quantity. It depends upon the geometry of the conductor and also on the permeability of the space. And it is independent of V or Q. So you cannot change the capacitance as by changing V and Q. Actually, it is the proportionality constant between V and Q, and it is constant for a constant device in a given medium. Now, the unit of the capacitance, as you can see from here, is, capacitance has units of coulombs per volts, okay? But we call this unit the farad, after the scientist Faraday, of course. But farad is a huge quantity, as we will see, and we usually use millifarads, microfarads even millifarad is a large quantity, sometimes microfarad, picofarad, or nanofarad. These are usually the sizes of the capacitances used in practical applications. Now, to give you an example how large is the farad, let's consider the capacitance of the Earth. And you can think of the Earth as if you think of the Earth as a conductor, for example, and this is as a spherical conductor. This is the capacitance of a spherical conductor. And substituting these constants here, epsilon naught and the radius of the Earth, you get the capacitance of the Earth as 7 times 10 to the power minus 4 farads, which is just 0.7 millifarads. So a conductor as huge as the Earth will have capacitance less than 1 farad. Okay, so this gives you an idea how large is the farad, and this is why we use actually micros and picos and nano farads. Now, let's talk about capacitors, introduced capacitors, which are devices used for storing charge and as such storing energy, as we will see. A capacitor consists usually of 2 conductors, so this is a condition. And these 2 conductors are called, each conductor is called a plate, so, or even if not be a plate, okay, but usually they are called the plates. And the conductors carry equal and opposite charge. Okay, this is how the capacitor works. So you have plus Q, for example, on one plate and minus Q on the second plate. So this is how you define a capacitor. And as such, when you have 2 conductors carrying equal and opposite charges, of course, there will be an electric field in the space between these 2 conductors. The electric field will be generated, and therefore a potential difference will be generated also. Okay? When you have electric field, you have potential difference. So now, therefore, we can, since this is a conductor, these 2 conductors, they carry a charge, okay, and there is a potential difference here, we can define the capacitance. We define the capacitance for a capacitor in this case by saying that the capacitance is the charge Q, the absolute value of the charge, which is the charge on one of them. We take it as positive because it's the same. The charge here or there, it's the same, positive or negative. So we take it as a positive quantity and divide it by the absolute value of the potential difference, okay, between them. And this quantity is the capacitance in this case. It's just like what we have done in the case of a single conductor, except now the potential here is the potential difference between the plates of the capacitor. The potential difference between the plates of the capacitor. The charge is the charge on one of them, any one of them, the magnitude of that charge. Okay, so this is the capacitor. Now, because I always substitute Q as positive and delta V, I take it as the absolute value of the potential, then in this case the capacitance is always a positive quantity. We don't have a negative capacitance. That has no meaning. And it's a constant, just like the case of one conductor. It's a constant independent of Q and V. This is what I mean. If the dimensions of the capacitors are not changed and the medium is not changed, the capacitance remains the same. And if we try to understand what does it mean, I mean try to make sense of the term used, which is capacitance, because you know this term I mean raises the intuition that there is something and you are stuffing thing in it, and what is the capacity of that thing. So actually exactly this is not far from what's going on here, because the capacitance is a measure of the capacitor's ability to store charge. Okay, and if you look at it here, it is actually how much charge, because it's Q coulombs per volt. So it is how much coulomb you need to store in order to raise the potential difference between the plates by 1 volt. So it's related to capacity actually, because you store charge and to raise the potential. Okay, so if a capacitor has higher capacity than others, then it needs more charge in order to raise the potential by 1 volt than another capacitor which has less capacitance. Therefore, the word capacitance here makes sense here. Okay, so the one which has larger capacitor can store more charge until the potential across its plates rises by 1 volt. Okay. So that's it. Before we proceed, you just consider that, this checkpoint and make sure that you do it. Okay, now we see how we calculate the capacitance of a capacitor. What we have been doing so far was generalities, defining the capacitance and so on. But let's now consider 3 examples. Start with parallel plate capacitor, then cylindrical capacitor, then spherical capacitor, and see how we can calculate the capacitance of each of these devices using the definition of a capacitance as the ratio between Q and delta V. So the first thing that we start with is a parallel plate capacitor. As we are familiar with this probably now, the parallel plate capacitor is just 2 large plates connected with a battery maintaining a constant electric field between them. Okay, maintain a constant potential, and constant potential means uniform electric field between them. Usually the plates are the plate dimensions are large in comparison with the distance between these. Now, what is the electric field? We want to find what is the potential, although we know it, but let's review it quickly. What is the electric field? The electric field is the charge density on one of these divided by epsilon naught, okay? And it's directed from the positive to the negative plate. This is what we know. Now, sigma is just Q over A, the total charge on one of the plates divided by the area. Now, what is the potential difference? We know that the absolute value of the potential difference for a uniform electric field across a distance d, it is something that we have calculated before, and we know it is just ED. Substituting for E from here, you get this is your potential difference, and therefore now we are ready actually to calculate the capacitance, which is the ratio of the charge to the potential difference. And if you do this, you get this expression here, and telling you that the capacitance is epsilon naught A over D. So the capacitance here depends, as you can see, on the permeability of the space, filling the region, permeability of the material, the medium, filling the space between the plates, multiplied by the area of the one of the plates, surface area divided by D. Now, the capacitance usually goes as follows. It's the units of capacitance. It's like epsilon naught multiplied by a unit of length. So as you can see here, you have length squared divided by length. We end up with length. So it's just epsilon naught multiplied by length. This is the usual unit of the unit of any capacitor, and this can be used in checking your calculations dimensionally. So again, as you can see, to increase the capacitance here, you increase the plate separation, and also you can decrease the distance between the plates. This is how you can increase the capacitance of this capacitor. Consider this checkpoint, which is an interesting application of parallel plate capacitors. The second example that we will consider is that of a cylindrical capacitor. And the cylindrical capacitor, as you can see in the figure here, consists of an inner cylinder with radius A, and we have an outer cylindrical shell. Both of them are conductors. We usually put the positive charge, in this example, with the positive charge is carried by the inner cylinder, and the negative charge is carried by the outer cylinder. Of course, this need not be the case. I mean, it could be the other way around. And the electric field lines, as you can see, this is a cross-section of this cylinder, and the electric field lines are radially outwards, as you can see, and we have worked out the electric field using Gauss law, so we know now what is the electric field in the region between the two conductors. It might be good to mention here that the practical everyday example of cylindrical capacitor is what we call the coaxial cable, which is just the the antenna wire of your TV and so on. It's composed actually of an inner cylinder, which is this tiny wire, and it's surrounded, however, by a plastic, which is a dielectric. We will talk about this later, and the outer grid that you can see in this line is the outer cylinder. So this is an everyday example of a cylindrical cylinder capacitor. The electric field is this, and it's directed radially outward, and as you can see, we have cylindrical symmetry, and it depends only on how far you are from the inner cylinder. Now, also, in calculating these, the capacitance of this cylinder, we are actually doing a good exercise in finding the potential when we have the electric field. Now, we mentioned when we discussed the electric potential, how to find the electric potential of continuous charge distributions, that one way of doing it also, when you know the electric field using Gauss law, for example, is to apply, to integrate the electric field between 2 points and find the potential difference. And this is exactly what we are going to do in this case. So I want first to find the capacitance. I have to divide Q by V. So what I do is I need to find the potential difference between these in this region. So I construct this integral because VB minus VA is just this integral, as we know. Now we have E, okay, the electric field, which is just this. So since we know it, we just plug it in. And note that since this integral is independent of the path, I choose the best path. The best path in this case is taking dr along r hat. And if you do this, and ds, I mean, is just dr r hat. This means that E dot ds will be just r hat dot dr. Ds will be just dr. Okay? And instead of Vr, you just substitute, it's the expression, and everything is constant. You take these outside the integral, and you have only an integration over dr, which is a simple integral, which is del n. So this is your potential difference in this region. Now, B is larger than A, and so to do this minus sign, this is a negative quantity. Okay? So VB minus VA is a negative quantity, but this is only what we expect. Why? Because, you know, you are moving here along the electric field line, so you are going into a potential drop. Okay? But in finding the capacitance, what we substitute here actually is what? Is the absolute value of the potential. So we keep this in mind, and this is why we substitute it actually without the minus sign here. When we take the absolute value of dV, this is the meaning of the dV that appears in C. It is the absolute value of the potential difference. And Q, a positive charge. Okay, so if you do this, this is the expression that we have for the potential. Now it is L over K, it's length over K, or because K is 1 over 4 pi epsilon naught goes up, so it becomes L times epsilon naught. This quantity is dimensionless. So this is the expression for the capacitance of the cylindrical capacitor. It depends, it increases by increasing the length of the cylinder or by increasing the ratio of between the outer the ratio between the radius of the outer cylinder to the inner cylinder. So you increase one of these, and this is how you change the capacitance. I mean, not okay. So you alter the capacitance by either altering this or altering this ratio, and we can define the capacitance per unit length, and in this case you divide by L. And it will depend only on the ratio, in this case, between B and A. Now, the other example, and the last example that we will find its capacitance is that of a spherical capacitor. And this spherical capacitor is composed of two concentric spherical conductors. One of them is a sphere. This might be a shell also, of radius A, and the other one centered at the same point but has a larger radius B. Okay? And this is how it looks. Again, we took the positive charge to be on the inner sphere and the negative charge to be at the outer sphere, and we want to find what is the capacitance of this capacitor. Again, this is a good example of finding the electric potential in a region when we need the electric field from Gauss law. Now, from Schill's theorem, I know that the electric field outside this shell in this region is actually that of a point charge, and so this is the electric field in the region between these two capacitors. That's all you need in order to calculate their potential difference. So the potential difference can be calculated using this integral. Again, take ds radial, which will be just dr r hat, and therefore the integral will reduce to just er dr, where er now is this expression here, the magnitude of E. And if you do this, you will have an integration of 1 over r square, which is also a simple integral to integrate. And therefore, you find V, and this is, you can just express it this way. This is your potential difference. Again, if you look at this, this is a negative quantity because A is smaller than B, and this is exactly what we expect because B is at a lower potential in comparison to A, because the electric field points from A to from the inner sphere to the outer sphere. So this sphere is at lower potential in comparison to the other sphere. You have to keep in mind this and substitute the absolute value of this delta V when you calculate the capacitance. So this is what we do here. And so when we take the absolute value, this is the expression that we get for the capacitance of a spherical conductor. And as you can see, the only thing that it depends on, this is K, which contains pi epsilon naught, and the other are the radii of the two spheres that form the capacitor. Again, this is either length over K, because this is length squared divided by length, so it becomes length over K, or if you substitute K as 1 over pi epsilon naught, this will be length multiplied by epsilon naught. Okay, so this is so dimensionally this is also okay. Now, of course, the obvious limit is when the length, the radius of the outer sphere goes to infinity. In this case, consider this when the radius goes to infinity. That's when B goes to infinity. You divide all the way by B, and in this case, A over B will go to 0 in this case, and divide up and down by B. So you'll get A 1 minus A, and therefore this is what will survive in this case, because B cancels out, and this is what survives in this case. Okay, so as you can see, you get the result for a sphere. That is the capacitance of a single sphere. This is what we expect. Now, some notes about the graphical representation of capacitors and circuits which involve capacitor. Usually, this is the symbol that we use for capacitor and circuits. And in circuits with capacitor, we have battery, and usually the battery is shown by this symbol. And they always have, we usually have switches when we have circuits with capacitor, and this is the symbol for switch. This is an open switch. This is a closed switch, of course. These symbols we will encounter when we consider circuits in future chapters.